Could you explain what a liquid metal is and what unique properties or behaviors they have over our traditional metals?
Sure. As you had mentioned, metals, you would typically characterize them as being hard, rigid, ductile materials that can conduct electricity, can conduct heat, and are used for structural applications. For liquid metals, these are materials that tend to be liquid at the room temperature, and they consist of a lot of different types of low melting point elements. Gallium is one of these types of elements. And when people hear of liquid metals, they typically think of a mercury thermometer, so like the kind that our parents probably used to use, but also the T1000 Terminator. We're not quite there yet in terms of how we can...
Hello, everyone. Welcome back to the It's a Material World podcast. I'm your host, Puneet, and alongside me is David. What's new in your world? I think it's been a little while since we've jumped on a podcast, and what's going on?
Yeah, it's been a whirlwind over here. I've been traveling for work, so I've gone to San Diego a few times, which is fun. It's a lot of time when you have to travel, so it was fun the first couple of times, but we'll see how many more times I go. But no, it's been pretty good over here. How about yourself?
Yeah. Oh, well, also a lot of travel. So apologies for the brief hiatus in terms of not releasing a podcast episode on our typical Material Mondays. But yeah, I was in Chicago for a week, not traveling for work or anything, just exploring the area, and it was a ton of fun. It was good to kind of get that relaxing break away from everything, no commitments whatsoever. And yeah, it just started to kind of warm up here in the Midwest. So it was an opportune time to get away. So yeah, it seems like we've both been traveling, but now we're both back into the normal routines and had time to jump on a late night podcast recording where we discussed with Wilson basically the world of liquid metals, and specifically he operates with gallium based liquid metals for applications in electronics. And so just kind of to bring it back to maybe something that's a little bit more relatable, or maybe a video you all have seen. One thing that was memorable to me was using gallium, just the liquid metal, to basically melt a soda can, aluminum can. Basically, it embrittles it and it makes it really easy to kind of just tear apart. So we dive into that phenomenon a little bit in this podcast, and then discuss, how does that research enable future applications? What does the space look like? So David, what was your favorite part? What's something that our listeners should look out for?
Yeah, I think Wilson is also a listener, so it's great to have the people who like to listen come on the podcast. But yeah, I think Wilson was just super knowledgeable, and it just shows because he's only a postdoctorate graduate researcher, so he's really not much older or younger than us. And so I think that it's really just great to see how dedicated he became to the field, and he is super knowledgeable. We threw him a bunch of questions that we did not prepare him for, and he really knew all the stuff. But the stuff he talked about was super interesting as well. And I think the applications of liquid metals and some of the coolest stuff was the liquid metals are used for conductivity, and you can encapsulate them so that they don't embrittle the metals around it, but can be broken by strain. And so you can have conductivity as you strain a material, and just a elastic response and a dynamic response he talked about is extremely cool, as well as a bunch of other things that he talked about. So it's just really interesting to see the potential future, especially because it seems like we're on kind of the cutting edge right now before it starts to get more steam in the actual world.
Yeah, the commercial world. Yeah, for sure. And so I just wanted to add on to that. It was one tidbit that he added, which was cool relative to with traditional metals. If you strain the metal, then you lose out on its, I believe, resistance or resistivity. But with the liquid metals, it seems like that conductivity remains the same, or that resistance remains the same, even when you strain the material, it doesn't lose out, and you can strain it up to 300%, which was incredible. Even though Wilson's research primarily focuses on soft electronics and functional liquid metals. He has a very extensive background in this space, so he really gave us a thorough idea of the different other applications, 5 years down the line, 10 years down the line, et cetera. And, I'm in the biomedical space. So when he talked about the sensing applications, biosensors, et cetera, it was all super fascinating. And I think it's all worth a listen. And finally, he really wraps up with some valuable advice that I couldn't agree with more, regarding like what MSE students should do, or what should their perspective be in college and beyond, so that they can make an impact in their respective research fields, not even just specific to liquid metals. So it's a lot to dig into, so we'll get right into it. But just remember, we would really appreciate to leave a rating and review on your preferred podcast platform. That means the world to us. So without further ado, let's get into it. Hello, everyone. So for today's episode, I'm happy to introduce Dr. Wilson Kong, an expert on functional liquid metals. Wilson obtained his bachelor's in material science and engineering from the University of Arizona, then moved on to earn his master's and finally his PhD in 2021 from Arizona State University, specializing in liquid metals, thermal interface materials, and 2D materials. He is currently a National Research Council, or NRC, postdoctoral researcher at the Air Force Research Laboratory in Ohio, where he applies his expertise to cutting-edge research of functional liquid metal nanomaterials for soft electronics. Wilson, thanks so much for coming on the show.
Yeah, thanks for the invitation. Happy to be here.
Awesome. Let's dive right into it. So maybe you can first off explain something to us. So it's somewhat counterintuitive to use liquid metals for a functional purpose. The traditional reasoning is to use metals to ensure you maintain strength, shape, rigidity, and so on. Could you explain what a liquid metal is and what unique properties or behaviors they have over our traditional metals?
Sure. As you had mentioned, metals, you would typically characterize them as being hard, rigid, ductile materials that can conduct electricity, can conduct heat, and are used for structural applications. For liquid metals, these are materials that tend to be liquid at the room temperature, and they consist of a lot of different types of low melting point elements. Gallium is one of these types of elements. And when people hear of liquid metals, they typically think of a mercury thermometer, so like the kind that our parents probably used to use, but also the T1000 Terminator. We're not quite there yet in terms of how we can make liquid metals into robots, but maybe someday, in maybe a few years. I think that these materials, they tend to have a lot of interesting properties because they are metals, but they also are liquid, and they can be applied in a number of soft applications. So these liquid metals typically consist of gallium, indium, tin, or zinc, or any combination of these alloys. And typically the broader classification for liquid metals are elements that melt under 300 C. That's generally a low bar when it comes to materials processing. So oftentimes you see metals having melting points that are in excess of 1,000 degrees. So in this case, having these low melting point alloys give you opportunity to obtain very interesting properties at room temperature. So these liquid metals typically have a few key characteristics, which I will categorize into two separate categories, one related to the spreadability and the other related to reactivity. So the spreadability of these materials, these liquid metals tend to be very low viscosity fluids, so they flow very easily, much like water. And they also have very high surface tension. So much like the surface tension of water on the surface, where you could see it wetting a surface, these liquid metals tend to bead up and maintain a spherical shape because of this high surface tension. And these liquid metals also tend to be non-wetting for certain surfaces. So they have very particular interactions with certain substrates. With metals, these liquid metals tend to have chemical interactions and form reactive alloys across the interface. And this enables a process called reactive wetting to occur. And in other cases, the liquid metal just doesn't wet the material at all and stays in a more spherical shape. And on the reactive side of liquid metals, a key aspect of these materials is that they can oxidize very quickly. So much like if you leave a glass of milk out for too long, a small thin film or skin forms on the surface of the milk. And this is exactly what happens with liquid metals as well. They form a very thin, around 3 nanometer oxide skin on the surface. And this oxide is very mechanically robust despite being so thin. So we can actually use this oxide for many different types of processing applications when it comes to working with liquid metal. And aside from the oxidation on the surface, we also can have these liquid metals alloy with other materials. So for instance, if you were to take a liquid metal and combine it with other transition metals such as copper or silver, they can form what's called intermetallic alloy species. And these intermetallics tend to form very rapidly and spontaneously. And depending on the composition of the alloy, this may change the overall properties of these liquid metals. And lastly, one very important aspect of these liquid metals is that because they're so reactive, they can also be detrimental to other materials. So a classic example would be liquid metals in contact with aluminum. So you guys have probably seen videos online where people can put a droplet of gallium on an aluminum can and it completely eats right through it. And this occurs because the gallium in its liquid state diffuses through the grain boundaries, so the different crystalline interfaces between grains in the material. And these processes cause the material to embrittle. So this would cause very detrimental mechanical failure of the material, so going from a ductile to brittle transition, essentially. So these are very important aspects of liquid metal, and understanding each of these would enable us to have a better toolkit for designing liquid metals for other soft applications.
I appreciate the thorough background on liquid metals, and we'll dive into potential applications soon enough. But when you talk about some of these properties, they remind me of polymers in a way, and I would love to get kind of a breakdown on the specific properties of liquid metals versus polymers in terms of their similarities and differences and potential applications as well.
Yeah. So polymers are traditionally seen as very soft materials. And if you think about it, our human body is made up of a lot of soft matter material, so a lot of biomaterials, and they're intrinsically deformable and stretchable, yet we can accomplish so many things with our human body. We can actuate and grab things with our hands. We have sensors in our eyes and our ears, and all of this is enabled through soft materials. And in this sense, it's important to start looking at more applications in the soft material space, which is why polymers become so important. And polymers are typically characterized as being chains of monomers that are linked together through chemical bonds. These polymers generally are tangled up in sort of coils and can be stretched and elongated without losing any of their mechanical integrity. So these polymers can be used for a lot of these stretchable or flexible applications. However, they tend to not conduct electricity very well. So they're insulating materials. And there are some efforts out there. Some of the work done in Jed and Bao's group at Stanford University have been looking at stretchable conductive polymers or semiconducting polymers. And they try to engineer these polymers at a molecular scale to have crystalline regions that can conduct electricity or other carriers very well and still maintain that stretchability that is characteristic for polymers. And compared to liquid metals, we can start taking advantage of the fact that because it's in its liquid state, we can deform the material and we can apply it in concert with different polymer substrates and create composite materials that not only have the stretchability of polymers, but also now have conductivity due to the liquid metals. And there has been a lot of integration in different forms for these types of materials. And one classic example is looking at patterning traditional metals with a serpentine pattern onto polymer substrates. And this is typically how people can achieve a stretchable or wearable device that can deform and still maintain conductivity when it's stretched. But with the case of the liquid metal, we can take these materials and essentially deform them, or we can take these liquid metals and turn them into micro or nanoscale particles and then develop inks, which we can then use as conductive materials for other stretchable applications. So there's certainly a lot of opportunity areas when it comes to looking at how liquid metals are similar to polymers and their soft aspects, and how there could be synergies between the two different materials.
When we talk about liquid metals, what is the normal like temperature range that like we're talking about? Because all metals can be liquid, but is there a specific temperature range that you're talking about? And then out of all the metals, like how many can actually like survive in this range that would be useful for actual applications?
Yeah, so I'll give you a couple of specific examples. So a liquid metal alloy that I typically work with is gallium indium eutectic, or EGAIN for short. And this is a material that in your introduction to material science classes, you typically see this as like an example phase diagram where they show gallium indium and then where the liquidus and solidus phases are. And what's interesting about this alloy is that at a specific composition, usually around 75% gallium and 25% indium, is where it reaches a eutectic temperature. And this is where the alloy reaches its lowest melting point. And typically the EGAIN has a melting point of around 15 C, which is definitely below room temperature. And this enables additional functionality of this liquid metal where we can use it at room temperature and not have to worry about it necessarily solidifying or having any rigidity issues. There are other liquid metal alloys that can combine other materials to further depress or increase its melting temperature. So another common alloy is gallium, which is EGAIN, but with the addition of tin. And usually with this addition of tin, it actually further depresses that melting point to around 11 C. So it drops about 4 degrees. And there have been some studies that had reported a melting point of minus 19 C, which is generally what is reported for industry related materials. There's a company called Germatherm, which I think was like one of the first to manufacture gallium on a large scale. And one of their MDS sheets had reported a melting point of about 19 C or minus 19 C. So I think that it's pretty incredible that there are metals that can potentially be depressed to that low of a melting point. To that end, liquid metals that have been processed into particles, and these particles are core shell in nature. So there's a liquid metal core, and then the outside is encapsulated in an oxide. And what's interesting is that these particles actually can undergo supercooling. And this is an effect where the material reaches a temperature below its freezing point, but it doesn't actually freeze. It still stays in its liquid state. And a large part of this is due to the fact that there's no nucleation of a crystal when the material reaches those low temperatures. And this means that there's no point at which the material can solidify. So that offers some very interesting behavior in that we can have these liquid metal capsules that then remain in the liquid state far below its freezing point. And this gives it additional wiggle room in terms of different application areas. So there are many different types of room temperature liquid metals, but there are also some that are interesting that are just above room temperature. And a common alloy here is called Fields metal. And this is a metal that consists of bismuth, indium, and tin. And this alloy has a melting point of around 68 C. So it's definitely above room temperature. But it also is low enough where people can still mildly heat the metal or whatever the metal is attached to and still be able to achieve the types of functional applications that they're looking for. So there's certainly a wide variety of temperature ranges in terms of how we can use these materials.
Interesting. So you mentioned the supercooling, and I was just curious about that from the processing potential of it. Can you talk about what applications, what effect that enables, and then just the processing of these liquid metals in general, if there's any challenges there that we're facing?
Yeah. So first, let me give you guys a background on some of these liquid metal particles that I've been talking about. And oftentimes people use mechanical agitation or shear mixing in order to take a bulk liquid metal and turn it into micro or nanoscale particles. And this occurs because of how fast the surface oxidizes. So if you were to take a bulk liquid metal and put it into a solvent medium such as ethanol, you can probe sonicate it so that it can turn into discretely encapsulated particles. Now, these particles are highly spherical and they can certainly change in size and shape the longer you sonicate these materials, but they can also achieve the supercooling effect simply by having that encapsulation and having essentially a barrier that prevents the liquid metal exposure to its external environment. And if you were to take a closer look at these particles, then you could imagine that this skin of the oxide on top of the liquid metal is atomically smooth. So generally, if you were to solidify a material, you need some nucleation point, a defect, or a speck of dust. In the case of water, if you were to freeze water. And the case of these liquid metals, they tend to have nucleation-free zones. So these liquid metals can stay liquid even if you lower the temperature far below its freezing point. So from a processing standpoint, this certainly offers a lot of interesting avenues in producing particles for functional applications. And these particles can also be linked together by organic ligands, and they can be polymerized and cross-linked to form stretchable conductive traces. So one of the innovations from our lab at the Air Force Research Laboratory, we have developed a polymerized liquid metal network. And this is essentially an electronic ink that could be deposited onto a stretchable substrate. And this material, you can actually stretch it to 100 or 200, 300% strain, and it does not lose any of its conductivity. In fact, its resistance actually doesn't change. And this is counterintuitive compared to other traditional metals, since these metals tend to increase in resistance as you increase the elongation and decrease the cross-sectional area. So this offers a way to potentially develop stretchable conductive materials that are all enabled because we can take advantage of liquid metal oxidation to make particles and then functionalize those particle surfaces to create these novel application areas.
So you talked about supercooling and the cold side of processing. What about at higher temperatures? How does that affect maybe the viscosity or rheology of your substance, and how do you overcome these challenges?
Yeah, that's a great question. So generally, these liquid metals, one of the main concerns is that do they evaporate? And that's certainly a question for any liquid. At some point, the liquid will have to turn into a gas. And luckily, these are materials that have very low vapor pressure. So you will not expect them to outgas or turn into its gaseous phase until very, very high temperatures. And I think the temperatures are generally on the order of maybe 2000 degrees C. So it's a pretty high bar to clear in terms of operating at high temperature and having to worry about any toxicological effects. But for the most part, I think that these liquid metals tend to be used at room temperature applications, but there are also other applications in which they may need to be used at elevated temperature. So one of the aspects of my PhD is working on thermal interface materials. And just to give you guys a background, the semiconductor industry obviously makes a lot of microelectronics chips, and they're found in our everyday devices. The computer that we're using to have this call, our cell phones, our automobiles, and other types of electronic devices. And these devices, as they operate over time, they tend to generate large amounts of waste heat. And this heat could be very detrimental, not only to the device operation, but also the performance of the device. And eventually it can also degrade the device if you were to overheat the material for too long. So in this case, thermal interface materials are important because they help bridge the gap between different components between microelectronics package components. And they enable an interfacial heat transfer across, say, the heat spreader and also heat sink that are attached to the silicon die, which usually are used to cool the material. And one of the main challenges of using liquid metal is the fact that it's very high surface tension, and the materials tend to not spread very well across the silicon die. So we want to be able to address these issues and replace current commercial TIMs, which tend to face challenges of their own with thermal resistance, with compatibility, and also materials degradation. And liquid metals could be a good way to solve these issues and potentially be used as a thermal interface material themselves. And typically these operating temperatures can go past 100 C. So you want the material to still have stability at higher temperatures and also not be able to outflow or pump out during thermomechanical cycling. So when you have the computer turn on and off and it goes under different temperature cycles, this could cause thermal stresses, which could cause liquid metal to leak out. And in this case, you want to be able to arrest this movement by increasing the viscosity of the liquid metal. So one of the ways that I try to address this problem is to essentially make the liquid metal more viscous. And we can do this through a number of ways by incorporating different types of filler materials into liquid metal. So what do I mean by this? A filler material is something that we can use to incorporate into liquid metal and essentially turn it into a composite. So a combination of two different types of materials that serve a functional purpose. So in this case, we looked at creating liquid metal-based foams and being able to inject air into liquid metal. And we can accomplish this by essentially stirring the liquid metal in air, and the oxides that form on the surface, they actually fracture and incorporate themselves into the liquid metal, thereby decreasing its surface tension over time as we incorporate more and more filler. And eventually, the stirring process actually causes air to get trapped in the liquid metal. So we can essentially form something that has a foam-like or porous structure. And this creates a paste-like material that is less easily able to flow and is able to adhere better to different surfaces. We can also accomplish this by adding solid particles into liquid metal and having these materials not only provide additional thermal conductivity, but also being able to improve the viscosity and the rheological properties of the liquid metals. So having these in mind, we can see that having high temperature applications for liquid metals, that's certainly a very important application area in which we can still have a lot of opportunity to grow and find new innovations.
So taking a step back, we've talked a lot about like electronics and the potential of liquid metals in this space. Are there any other application areas you see liquid metals making an impact in the future? And if so, what would be some of those challenges that need to be overcome to enable these applications? Because I know one thing that I've been curious about is you mentioned how gallium, for example, could embrittle some of the materials it interfaces like aluminum, right? And there are a lot of application areas that utilize different material classes. So one question I had is, how do liquid metals not negatively impact the other material classes in certain applications? So I would just love to hear your thoughts there.
Yeah, and I think that because liquid metal space is becoming more of an emergent field, there's certainly a lot of challenges that we would need to address in order to find additional application spaces for these materials. And just to talk a little bit more about the thermal interface materials and some of the challenges that they face, you're definitely right that the liquid metals have a strong tendency to embrittle other materials such as aluminum. And this is very detrimental since aluminum is a very common semiconductor industry material. So certainly you don't want to apply these liquid metals onto a very expensive computer chip and then find that it's completely destroyed because it's in contact with an aluminum component. So one of the ways that people have been trying to find ways to address this is to encapsulate the liquid metal in some other material. And generally, this is a polymer or a silicone oil that you can incorporate liquid metal into. And this serves as a barrier coating or a barrier layer to prevent direct contact of liquid metal onto other surfaces. So this has been a very common way to not only create a different composite material, but also have an opportunity to protect other surfaces from liquid metal. And a lot of the application spaces for liquid metals have been geared towards stretchable electronics. And the reason this is important is as the wearable space starts to grow, so having smart clothing and having physiological monitors that can keep track of different vital signs and health conditions, and having just more integrated technology onto ourselves, we want to be able to have stretchable, conductive materials. And having these liquid metal particles or even bulk liquid metal can be very useful for interconnects and being able to have conductors that can deform without necessarily sacrificing performance. So this is a very important area that people have been looking into developing to see if you can start having more integrated and smart clothing and potentially having flexible hybrid technology, so integrated soft materials with traditional hard electronics. And this is something that an organization called Flex is starting to look more into and trying to find hybrid solutions where we can start combining aspects of soft materials with traditional hard materials. Another application area that I can think of for these liquid metals is use in catalysis. So some of the emergent works in the literature have been looking into using liquid metals for catalytic substrates and being able to not only catalyze reactions, but also transform materials. And what do I mean by this? So these liquid metals can also have been reported to catalyze CO2 into carbon. So this is very important as we are looking to fight climate change and trying to reduce our CO2 output. And having these liquid metals being another potential material to not only convert CO2, but also being able to potentially capture CO2 in the air, this could have a lot of implications for how we can start addressing some of our primary climate concerns. And the reactive surface of liquid metals have been employed for synthesis applications. So as the material is a metal and a very conductive surface, electron-rich surface, you would imagine that a lot of reactions that require electron-rich surfaces could take place at the interface of liquid metal. And one classic example for these syntheses is to use a process called galvanic replacement. And this is a electrochemical reaction that is spontaneous and it takes place typically in solution where you have metal ions in solution. So let's say copper ions or silver ions. And it takes a look at the redox potential or the oxidation reduction potential between both the gallium and the metal ions are in solution. And depending on how favorable these reaction potentials are, you can spontaneously get the ions in solution to reduce and deposit on the surface of liquid metal while you have the liquid metal oxidize. So this is a way for people to form these core shell hybrid nanostructures that can be consistent of a liquid metal core and other materials deposit on the surface. And this offers a lot of interesting opportunity areas for new material synthesis methods. There's a group actually in Australia that has been working on two-dimensional material synthesis on liquid metals. And in your channel, I don't know if there's like a lot of 2D materials that have been discussed. I think there was an episode on vaccines and maybe some graphene episodes, but typically these 2D materials are low-dimensional layered structures that have very interesting properties depending on the number of layers or the chemical composition. So they offer a lot of interesting properties for semiconducting applications, for catalysis, for flexible electronics, and being able to synthesize them at large scale is a challenge that people have been trying to address for many years. And liquid metals have recently become a very popular method to synthesize these liquid metals, these liquid metals have been very popular to synthesize 2D materials at a very large scale. And one example here is the growth of molybdenum disulfide, which is a semiconductor, and this can be done very easily in a solution-based method for liquid metal. And it offers additional avenues that we can explore. And this is something that I'm currently doing in my own research and trying to explore new ways to develop new materials utilizing the liquid metal interface. I guess another application area that is emerging right now is use in biomedical space. So liquid metals are non-toxic compared to mercury. And these materials have been used in both bulk and particle form for different biomedical applications. You can use them for sensing applications as physiological monitor or gas sensing or chemical sensing. You can also use them for drug delivery. So having these liquid metal particles being implanted into a living animal or even the human body and still be biocompatible and not have any particular adverse effects. This research is really new, so there's certainly a lot of room for exploration and for improvement. It's something that I certainly don't know as much about, but would be very interested in diving more into that space. So certainly there are a lot of application areas that could be utilized for these materials.
Yeah, maybe just in a few thoughts, and we can continue, is you mentioned that a common thing to do with the liquid metal is to encapsulate it in, you said, a polymer or a silicone-based wrap. The main function of liquid metals, if I understand correctly, is the conductivity. As strain increases, it doesn't decrease. But these polymers and silicone seem to be maybe counteractive, where it might decrease conductivity. Could you briefly describe that relationship?
Yeah. So this kind of comes down to materials processing and how you incorporate these materials into a polymer matrix. So one key aspect for creating stretchable conductive materials is having these liquid metal particles essentially being able to touch one another. So you would need to be able to fill this composite that you're making with polymer materials up with enough liquid metal content in order to enable this percolation network to form. And oftentimes these particles have the oxide shell on them. So you would have to rupture the oxide in order to enable conductive traces to form. And one method to do this is simply straining it. So you can stretch apart this composite and essentially form this conductive network as you're rupturing the oxide shells and enabling particles to coalesce and form a conductive network. So this is a key aspect of having stimuli responsive materials, because you have an external input and you enable some functional output. So in this case, turning your composite material from an insulating to a conductive material. And there are other ways that we can make liquid metals stimuli responsive that could be responsive to thermal inputs, potentially to optical inputs, potentially to catalytic inputs. So the list kind of goes on in terms of what we could do for quote unquote activating these materials. But certainly for the stretchable electronic space, we can still maintain the performance of the material, even though we're stretching it, by simply having the materials transition from insulating to conducting due to this percolation network formation.
So I want to go off on a tangent just for a moment, because I was very impressed with your background, and I saw that like at college and grad school you were heavily involved in the Society of Asian Scientists and Engineers, you know, starting as president and then later moving on to a kind of leadership committee role. And that's something else that we want to really harp on and emphasize in these types of podcast episodes. So can you just talk about briefly, before we kind of go back to the technical stuff, just what kind of impact and growth you saw as a result of your involvement in the society?
Yeah, and I have very fond memories of SACE, and because it really shaped a lot of my college experience and grad school experience. It certainly gave me opportunities to develop my leadership and professional skills. And I guess to backtrack a little bit and talk about what SACE is. So the Society of Asian Scientists and Engineers is a nonprofit organization that's dedicated to helping students and young professionals, typically of Asian heritage or Asian descent, to develop their leadership or professional networking skills and to achieve their full career potential. So oftentimes there's a stereotype that Asian Americans are very good at STEM fields, are good at math and science, and are able to go to colleges and essentially crush these types of environments. But oftentimes we tend to get overlooked with our leadership skills, and in the sense that there are a lot of groups out there that are trying to advocate for more Asian American representation in higher leadership positions and executive positions. And this is something that SACE wants to bring to light and also help students to achieve. So my involvement with SACE has held many different functions over the years. So I started as a chapter founder and the first president of the chapter, and eventually moved on to different national volunteer roles. And I think overall, I felt a large sense of service and wanting to give back, since I'm a first generation student to not only go to college to get a STEM degree, but also to obtain a doctorate. And this is something that I consider a very proud personal achievement. But I also want to be able to help other, not only Asian American students, but also other students in general to develop these skills and to help achieve their own goals. So being a part of SACE allowed me to have a platform in which I could get involved in committees where I could organize events to develop leadership workshops or leadership development content, and being able to disseminate that from the national level all the way down to the chapter level. And this is something that I've been very passionate about for many years. And while I'm no longer a volunteer, I stopped doing volunteering as of a couple of years ago, I still act as a collegiate mentor. So being paired up with different SACE members who are still in college and essentially trying to help them through answering questions and being able to navigate through all the different winding roads of college. And as you guys already know, it's a very chaotic time, especially if you're in a STEM program and having classes and clubs and all these things to juggle. So it's a very important to me to give back to my community. And this is one way that I've been able to do that. And I'm hoping to find other ways to do that as well.
Yeah, I think that's really great initiative, especially as just there's a lot of different people out there, and just giving groups of people empowerment is always good to give a more diverse and a more varied approach to different engineering results. And so I think that's a really great initiative. Maybe moving along and wrapping up today's conversation, I think you've talked a lot about all the great applications of liquid metals, and you've talked a lot about your own leadership abilities and your journey. Maybe looking ahead in the future, in 10 years, what challenges need to be addressed to enable the safe and efficient recycling or reclamation of liquid metals from discarded or obsolete devices? And then maybe how do you think that kind of changes how liquid metals look like in applications for the next 10 years?
So that's a great question. And looking ahead, I think one of the primary challenges is certainly recovering the materials, since gallium is not only used in liquid metal alloys, but it's used in a bunch of other types of materials. Some of the other common semiconductor materials that are used in industry, gallium nitride, gallium arsenide, obviously contain gallium. And there are also concerns with indium, because indium is a very expensive metal. And we also want to be able to recycle these materials for other applications. So in this case, this becomes a very important issue to deal with. And it's certainly something that I think people are starting to pay more attention to in terms of material recovery. And one of the ways that I can think of for trying to recover some of these materials is to perform essentially acid-based reclamation. So one of the key aspects of these liquid metals, as I mentioned, is their oxide. And you can actually remove the oxide layer by creating an acidic environment. And you can do this with, say, HCl or hydrochloric acid. And this acid effectively etches the oxide and takes all these freely dispersed particles that are in solution, and you can recoalesce them back into a bulk liquid. And this is something that is essentially repeatable. So you can take a bulk liquid, process them into particles, and then you simply put these particles in an acidic solution and remove the oxide to turn them back into a bulk fluid. And this is one good way to recover the materials from that aspect. But there are also other more industry standard practices, such as hydrometallurgy. And this is something that people have been using to extract metals from ore. And this is very common in the mining industry. And certainly they also have leaching processes within hydrometallurgy that take advantage of using some acidic aqueous solution that can be used to etch out or leach out other metal species. And sometimes this can be done selectively so you can get certain metals that you want. And I can imagine that these practices could be employed for these gallium-based liquid metals as well. So in general, I think coming up with different ways to not only reuse these materials for research purposes, but after they're spent in industrial applications or in electronics, we want to be able to recover these metals and being able to use them in future electronics. And I think that's certainly a very interesting problem to tackle, and I'm hoping to learn more about it myself one of these days.
Sure, for sure. And there seems to be a lot of research in this space and really pushing the boundaries. And so maybe to wrap up this conversation, first of all, thank you for your time and for sharing all of your knowledge regarding these liquid metals. Can we wrap up with your advice for what MSE students, the next generation of MSE students, what can they do to get involved in this field and continue to push the boundaries in terms of these future applications in liquid metals?
So I would first want to refer to a quote by the late Steve Jobs. And this was something that he gave at the Stanford University commencement address. And it's certainly a very popular video on YouTube. But here he says, you can't connect the dots looking forward, and you can only connect them looking backwards. So you have to trust that the dots will somehow connect in your future. And I really like this quote, not only for the context of his speech, but also the fact that we can find very interesting intersections between different scientific disciplines by looking at how your past experiences connect to one another. And this is sort of how I got into this functional liquid metal space, in that I worked on different types of nanomaterials and eventually moved on to the thermal interface material space and eventually moved into this functional liquid nanomaterial space. And I feel in retrospect that this was possible because I had the experiences that I did throughout grad school. And by connecting those research dots, so to speak, I was able to find connections and potentially developing new research directions. So I would say that for especially those who are starting college or not entirely sure what they want to do, just try everything. If you want to do research, if you want to do that internship, or maybe you just want to pick up a new skill, I think that you can't really plan ahead by looking forward, and that just simply trying things and doing what you feel is appropriate for you at the time, looking back, it might have some very interesting applications, or you might come up with some new ideas and improve that creative aspect that you might have. So I would say that for people wanting to get into liquid metals, there are definitely a ton of resources out there, a lot of scientific literature, and a few key figures in the liquid metal space. I want to point out Dr. Michael Dickey from North Carolina State University. He's definitely one of the most prominent researchers in liquid metal. And there are definitely many others, Dr. Rebecca Kramer, Dr. Carmel Majidi. These are all people that do very interesting soft materials or soft robotics research. And I would encourage that the listeners, if they're interested, to look up some of these people and to see if this is the kind of work that they might want to learn more about or get involved with.
Awesome. Yeah, that's spectacular advice, and really appreciate you coming on the show, Wilson. It was a pleasure having you.
All right, thank you so much. I really enjoyed my time here.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.